Whether am I audible to you now?
Audible,
Whether
sir.
the screen is visible?
Also breaking your voice. Okay, it's audible. Now your PPT also visible. Now start the session, sir.
Okay. Thank you very much for this brief introduction. And I would like to thank the management, principal head of the institution and the organizer for giving such an interesting opportunity to explore my perspective on advanced diesel engine combustion for clean combustion. So the overall session is scheduled in this particular fashion, where we will just start our session with a brief introduction, followed by I'll just make you to walk through the recent advancement in diesel engine combustion and various concepts that is lying with advanced diesel engine combustions, and a brief conclusion. Can you please mute the other participants, sir? Organizers. Okay. I would like to start the presentation with the recent news, so thereby you can just try to understand the current importance of this particular shock. Future keep on decreasing, and the price of crude oil is keep on rising. All put together, the role of diesel vehicle and the diesel-based fuel vehicle is completely getting a very shaky ground on this particular point of time. And sooner or later, the rest in peace of diesel engine-based vehicle is also going to like. So to make this diesel engine alive, what they are currently doing at this particular point of time is what my presentation is focused on. And researchers design new hybrid engines that are more efficient and less contaminating. So to make either diesel or petrol alive, they have just tried to transform this diesel and petrol vehicle into a hybrid vehicle mode. So only by the name of hybrid vehicle, sooner or later, the internal combustion engine will be alive for next 20 to 30 years, and as not as either pure internal combustion engine vehicle, that is pure petrol vehicle or pure diesel vehicle. And Honda is aiming to phase out its pure internal combustion engine from the European line in 2020. So you might have heard about the news related with Ford. So they have completely stopped with production based on internal combustion engine as of now. And sooner or later, Honda is also going to join hand with them. So all put together, they have started to initiate the importance of the decline of internal combustion engine at this particular point of time. And Volvo added mild hybrid vehicle and plug-in hybrid vehicle models for all its variant. So sooner or later, it is going to be for all the vehicles. So it was in 2010, only the internal combustion engine was ruling the entire automotive market share. So it was only the internal combustion engine was ruling the entire market share. But as the year keep on decreasing, you can just see the internal combustion engine would slowly start to get phase out. And the role of hybrid vehicle and plug-in hybrid vehicle would start its key role. So it aligns with that. As of now, we are in 2021. So by 2021, the penetration of the hybrid vehicle should have initially started to a minimal percentage. So with reliance with this, whatever the statistical data that I have said earlier, so Yamaha Fasino 125 is coming up with an hybrid vehicle mode. So the term hybrid vehicle mode talks about it will have both internal combustion engine and a battery plus motor combination. So the power would be delivered from both the internal combustion engine and battery plus motor combination. And this news was there in air by July 22. So it was there in air by July 22, 2021. So this statistical data is very much assured with whatever the recent research, the recent market share that is happening as of now in India. So after 2020, the penetration of hybrid vehicle and plug-in hybrid vehicle would sir. So could you please kindly mute the other participants? So it would be much more easier for me.
Yes, sir.
So after 2020, you can just see the penetration of hybrid vehicle and plug-in hybrid vehicle would reach its role at a maximum level, and slowly the internal combustion engine would start to get degrade. So that would what be the near future at this particular point of time. And talking about the history of hybrid cars, both have started their era in the same time scale. So nothing is under new horizon. Either it can be electric or pure internal combustion engine or hybrid. So all started their time scale at the same time period. So it was in 1832, the first crude electric vehicle was introduced. So it was in 1832, the first crude electric vehicle was introduced. And it was in 1893, the internal combustion engine was get commercialized. The gasoline engine was get commercialized. It was the time scale of 1893. And it was in 1901, the first hybrid vehicle was introduced. So it was in 1901, the first hybrid vehicle was introduced. If you just see this, all three vehicles origin, it has been close or more or less in the same time scale. It was in either in late 18th century or in the early 19th century. So the internal combustion engine hybrid and the electric vehicle have started its origin, but somehow the internal combustion engine was ruling the entire market field for past 100 years. So that is from 19th century to 21st century. More or less above 100 years, only the internal combustion engine was ruling the entire automotive market share. But after that, somehow people have slowly started to translate from the internal combustion engine to either hybrid vehicle or electric vehicle. And even though the hybrid vehicle was introduced to the human mankind in 1901, it was in 1997 the first mass production hybrid vehicle was initiated. So first mass production hybrid vehicle is nothing but Toyota Prius. So Toyota Prius was mass produced in the time scale of 2000. So it was in the year 2000 only the first mass production hybrid vehicle was introduced. So for past 100 years, only the internal combustion engine was ruling the entire world. And after that, the hero of electric vehicle comes into picture. It was in 2006, Silicon Valley based startup make a very big statement to the entire automotive market field. So it is nothing but the Tesla Motors were and Silicon Valley based startup at that particular point of time. Organizer, sir. So it would be much more convenient if you kindly mute the other participants.
Yes, sir. I am.
Okay, thank you. So it was in 2006, the first electric vehicle was started to make its big picture into the automotive market. So it was in 2006, and startup make a very big statement. So it is nothing but the Tesla Motors. So Tesla Motors says that they will just produce a luxury electric sports car. So they just mentioned they will just produce a luxury electric sports car. other automotive manufacturers to start to work on their particular EV or hybrid vehicle variant. So this is what is all about the history of either internal combustion engine or hybrid vehicle or EV. So to many countries in the world, there are at least three reasons to reduce the fuel consumption for car. So one major reason that comes into mind or strike our mind is nothing but the CO2 emission. So this CO2 emission is a major threat in the entire nation as of now. So when talking about the fuel consumption, the people would more or less talk about the carbon neutralization, and India is one of the most important country who is targeting more on the carbon neutralization. And apart from that, the import duty of the crude oil is keep on rising. So talking about the import duty, it is leading by China, followed by US, and India is having a maximum share of import of crude oil. So this import of cars is and so our rate keep on increase and make it over the thing that you. So what are the possible ways to a particular point of time? So talking about a pure internal combustion engine, you can just rely more on the aerodynamic part of your vehicle, where it will have a greater impact on your drag, and thereby whenever you reduce your drag, you will have an higher option to increase the fuel consumption. And next important parameter is the tire with the low rolling resistance. So rolling resistance would have an higher impact. And third one is the engine with higher efficiency. So our slide talks about this particular part where we will be focusing on high efficiency engine with reduced fuel emissions with advanced combustion techniques in an existing diesel engine. So the possible ways to reduce the fuel consumption as of now talks about the aerodynamic part and the rolling resistive part. And third important key point is the efficiency of the engine. So when talking about the battery powered EV, battery powered electric vehicle on the other hand possesses some advantage over the existing internal combustion engine, such as high energy efficiency and zero environmental pollution. And you should be very much clear about the term zero environmental pollution. So when you are talking about the electric vehicle, people are slowly started to switch from pure internal combustion engine to EV. So when you are getting to switch over from internal combustion engine to EV, so the demand for electricity would be keep on increasing. So when the demand for electricity is increasing, what actually happens is the demand that you give for the thermal power plant would get increased. The demand
efficiency and reducing emission. तुम्हाला याच्यात काय म्हणायचं आपण इथं त्याला काय सांगितलंय की फ्युएल जर वापरलं तर ऍटमॉस्फिअरिक पोल्युटन होईल आणि तुम्ही परत काय म्हणताय पुन्हा हे दुसरं पॉइंट एकत्र हा सिम्पली द मेजर रोड.
Thank you. So what actually happens is that would create an excess pressure on the thermal power plant. So to handle a very huge demand, the thermal power plant should run for an excess time, and this thermal power plant based energy source is nothing but the fossil fuel. So when you are just switching over from internal combustion engine to EV, only from user end, there would be zero environmental pollution. Only from the user end. And rather emitting emission from your own vehicle, the emission would be drastically increased from the thermal power plant. So that what talks about the zero environmental pollution from the user end. And next one is, however, the performance, especially the operating range per battery, is far less compared to the IC engines. So it would result in lower energy density of your battery than the gasoline. So talking about the energy density, so the energy density of gasoline is enormously high, which is no par equal with whatever the energy density of your lithium-ion batteries. So we should be very much clear about why people have started to think about making use of lithium-ion batteries as of now, because it has a higher tendency to lose an electron, and it would be much more efficient than whatever the other electrochemical series values that are presently present as of now. And talking about one greater disadvantage is the energy density, and next thing that strike our mind is nothing but the weight of the battery. So in earlier in the starting 19th century, people have started to think about making use of lead acid battery. So whatever the energy comparative to your internal combustion engine at the same time would result in a weight of an elephant that would be carrying along with you when you're just traveling in your electric vehicle at that particular point of time. Already your vehicle would have a huge weight, because that at that particular point of time, that was in 19th century, that was not a drastic material focus based engines. So weight reduction was not a major threat at that particular point of time. So even that, when you're just working on an battery or electrical vehicle at that 19th century, it result in excess weight of the batteries. And this weight of the battery have slowly stepped down from 10,000 kgs to 200 kg as of now. Even now, the battery weight is enormously high, but it is somehow equal with the weight of your internal combustion engine at this particular point of time. So these are the greater disadvantage that strikes into our mind when talking about the battery powered electric vehicle. So taking these disadvantage and converting it into an useful input, so people have started to think about making use of hybrid vehicle technology. So hybrid vehicle which use two power source, one is the primary power source and the secondary power source. The primary power source would be always the internal combustion engine, and the secondary power source will be your battery plus motor combination. So this would have the disadvantage, this would compensate the disadvantage of your internal combustion engine, and you will be able to enjoy the advantage of your battery powered EV. And talking about the types of EV, so this EV can be classified as a hybrid electric vehicle. So this hybrid electric vehicle is further branched out as series, parallel, and a series and parallel combination. So talking about hybrid, you will be using two energy source. One is the fuel plus internal combustion engine combination, and next one is the battery plus motor combination. So in case of hybrid vehicle, you will be making use of, and for refilling, you'll be making use of a petrol pump, and obviously you will have a battery plus motor combination. And after a hybrid electric vehicle, people have slowly started to think about the plug-in hybrid vehicle technology, where you doesn't need to rely on your internal combustion engine power to charge your battery. So people started to think about making use of external energy to charge your batteries. So that come the importance of plug-in. Next one is pure electric vehicle. So where the internal combustion engine would completely get cut off, and people would be relying only on the electrical energy and the motor for propulsion. And next, rather relying on the electrical energy, people have started to making use of hydrogen and the solar as the futuristic source of producing electricity. So this is what going to be the future vehicles as of now in India or in the entire nation. So when talking about the hybrid vehicle, it is mainly classified in terms of two parameters. One is by the term of degree of hybridization, and other one by the term of energy flow. One is by the term of degree of hybridization, and other one is by the term of energy flow. So in terms of degree of hybridization, it's classified as micro hybrid, mild hybrid, and full hybrid. So what is this degree of hybridization? So the term degree of hybridization says that how much amount of electrical energy is going to delivered from your overall energy demand. So assume you are having an vehicle which is an hybrid vehicle. So that means it makes use of both combustion engine and battery plus motor combination. And the objective is you are having an n-wheel demand of 100 kilowatt power. So you are having an n-wheel demand of 100 kilowatt power for your propulsion of your vehicle. So if this 100 kilowatt power is delivered only from your pure internal combustion engine alone, then your degree of hybridization is 0%. And rather, this 100 kilowatt power is delivered only from your battery plus motor combination. If it is delivered only from your battery plus motor combination, then your degree of hybridization is 100%. So 100% of degree of hybridization is nothing but the pure battery electric vehicle. So that means your n-wheel demand will be only delivered by your battery plus motor combination. So the in-between percentage talks about the degree of hybridization. If you are having a demand of 100 kilowatt power, and if 75% of power is delivered from your engine plus internal combustion engine, and 25% of power is delivered from your battery plus motor combination, then your degree of hybridization is 25%. And if battery plus motors contribute 50%, then your DOH is 50. And if it is 75, your DOH is 75. So based upon this DOH percentage, it is classified as either micro hybrid, mild hybrid, or full hybrid. So for micro hybrid, the degree of hybridization would be 0 to 10 percentage. For mild hybrid, it would be 20 to 30, and for full hybrid, it would be 30 to 50. So at any point, the degree of hybridization would not exceed 50 percentage. You will try to understand why it doesn't exceed 50 percentage, because if the percentage of 50 exceeds, then the primary energy source would be your electric vehicle plus motor combination, and your secondary energy source would be your internal combustion engine. So the main objective of hybridization is to make your internal combustion engine alive. And then to make your internal combustion engine alive, the percentage of 50%. So at no point of time, they won't exceed the 50% to be particular. It would be 49.99%. At any point of time, the percentage of power that would be delivered from your battery plus motor combination would not exceed 49.99. If it exceeds 50, then your battery plus electric motor would become your primary energy source, and internal combustion engine would become the secondary energy source. Just to make the hybrid, a mild hybrid, and full hybrid. So whatever the vehicle as of now in the automotive market field is all micro hybrid vehicle. So think about the yearly vehicles that you have in your home. So for an assumption such as TVS XL. So for your TVS XL, you will have a kickstart option. So you need to kick and start your vehicle, or your older Scooty Pep model. So older Scooty Pep or Scooty model would have a kickstart option. So when talking about this micro hybrid, you will have an existing internal combustion engine. Apart from that, you will have a motor. So this motor will assist and stop your vehicle. So this what talk about the micro hybrid. So when that means all the vehicle as of now, all the two-wheeler vehicles as of now in your market is all falls under the category of micro hybrid, which will have the degree of hybridization of 0 to 10% at the maximum. So these vehicles would have very minimal percentage. So rather using the power of internal combustion engine, just by using a starter motor, you will try to start your engine externally with an assistance of a battery plus motor. So this is what talks about the micro hybrid. And apart from start and stop operation, you will have a motor start and stop, and when it is just able to make use of the regenerative braking to charge your battery. So at the time of braking, your motor would be acting as a generator, and it would create an impact on the impedance of your motor that result in possibility of producing current, and that can be effectively used to charge your battery. So this what talks about the regenerative motor. That motor would be assisting you for your start and stop operation. Apart from it would be assisting you for your regenerative braking mode. So in both cases, the size of your internal combustion engine would not be varied. That is that you can just introduce a motor to your existing vehicle, and you doesn't need to change any part of your internal combustion engine vehicle. So that is the reason why most of the vehicle have started to come up with an micro hybrid variant as of now. But switching over from micro hybrid variant into mild hybrid variant, so apart from the motor that is used for start and stop operation and regenerative braking, it would be assisting you for a power assist option. So this power assist talks about, assume you are in a signal, there is a Scooty Pep, or for an assumption, let us take this particular vehicle itself. So in the earlier slide, I have talked about Yamaha Fasino 125cc, which is an hybrid vehicle. So assume at that particular traffic signal, what is an Yamaha Fasino vehicle is present over there. A Fasino vehicle is present over there, and a gear vehicle is present over there. So what actually happens is one signal is turned green. So the person would try to accelerate. So at this particular point of time, the end wheel demand would be raised. So in this particular case, the power would be delivered from both your internal combustion engine and from the battery plus motor combination to handle this end wheel demand. So the acceleration would be higher than compared to this nearby vehicle. So at this particular point of time, this would able to assist you for your start and stop operation, regenerative braking, and apart from that, it would be assisting you as a power assist component. So this what talks about the mild hybrid based vehicle. And when you are just switching over from micro hybrid to mild hybrid, you need to downsize the engine. So this is one of the key concepts when talking about the hybrid vehicle. So when you just try to focus on hybrid vehicle, what actually happens is, let me
பஸ்
just try to
சலான்
focus over
கொடுக்க
here.
கூப்பிடுறாங்க சார். 3 பேத்தையும் கூட்டிட்டு வா. எங்க இருக்கா?
Assume you are having a vehicle which weighs around nearly 200 kg for an assumption. It is pure internal combustion engine vehicle, and you have been asked to convert it into an hybrid vehicle. So when you are just trying to convert it into an hybrid vehicle, what you'll be trying to do is you'll be trying to add a battery plus motor combination into it. So what actually happens is the weight of the vehicle would get increased. So assume the weight get increased by 100 kg. So the weight is 300 kg. So whatever the would be wasted because of this increase in weight. So to reduce this weight, what they will be trying to do is they will just work on different components present in your existing vehicle. And one main conceptual idea is downsizing the engine. So downsizing the engine talks about, so downsizing engine has nothing to do with the engine performance. So it won't just pull down the performance of the engine. So simply it is a method to reduce the weight of the engine. So unless and until you keep the weight of your both internal combustion engine and hybrid vehicle same, you won't be able to enjoy the allowance of your hybrid vehicle mode. So the main objective of engine downsizing is to reduce the weight of your internal combustion engine to enjoy the allowance of your hybrid vehicle mode to minimum possible way and achieve the best breed to power to weight ratio. So the best option for power to weight ratio can be achieved only by this. So that talks about, assume your internal combustion engine would have a weight of around 65 kg and which would be able to deliver a power of more or less 65 kilowatt. What we'll be trying to do is you'll be trying to reduce the weight of your engine. So rather 65, here it would be 55, and more or less it would be able to deliver the same power output. So the weight has been drastically reduced and there is not a very big deviation in the power. So this is what talks about the engine downsizing. So one thing that can be achieved is just by introducing a turbocharger into your engine. So that is the reason why as of now most of the vehicles are coming with either turbocharger or supercharger incorporated into it. So the main reason for it is because of the engine downsizing. So this is a pictorial representation of an wastegate turbocharger, and people are also working on wastegate turbocharger, variable geometry turbocharger to enhance the power output by reducing the weight of your engine. So this one talks about the engine downsizing. So moving back to the classification, we have discussed about the micro hybrid, mild hybrid, and after mild hybrid, people have started to think about the full hybrid. So in case of your mild hybrid, the degree of hybridization would be till 30 percentage, and for full hybrid it would be 49.99 percentage. That means based upon your end wheel demand, only 49.99 percentage of power would be able to deliver from your battery plus motor combination, and the remaining power would be delivered from your internal combustion engine. So the main idea behind this hybridization is to make the internal combustion engine alive for next 20 to 30 years. So your internal combustion engine will be alive only by the name of hybrid vehicle for next 20 to 30 years. So when you just see this particular case, they have tried to even downsize the engine, whatever we have seen earlier. So from the conventional engine, they have minimally reduced the size of the engine, and after that they have reduced it drastically. So thereby the term downsize has comes into picture. After that, they have even further reduced the size of the engine. And when moving from full hybrid to plug-in hybrid, they have even downsized the engine to a greater percentage. So when you're just working on this downsize engine at a maximum percentage, the efficiency of the engine should be much more higher than your conventional internal combustion engine. So what are the possible ways to increase the efficiency, and what are the possible ways to work on the advanced emission control techniques is what the upcoming slide is going to be focused on. So when talking about full hybrid, it would be able to assist you in start and stop, regenerative braking, power assist, and you might have an short electric drive. A separate energy storage can be placed, and that can be used to active vehicle as a pure EV mode. And when talking about plug-in hybrid vehicle mode, so the energy storage would be somewhat higher than the previous full hybrid mode. So thereby you can just able to charge your battery from an external source rather relying on the power source from your internal combustion engine alone. And next is full electric mode, where the internal combustion engine would be completely eliminated. So by the name of uh, the hybrid vehicle, you can just pull your internal combustion engine alive till 2040. So till 2040, your internal combustion engine will be alive only by the name of hybrid vehicle and not as pure internal combustion engine vehicle. So this is what going to be the near future in the entire nation in the upcoming years. And we have discussed about what is engine downsizing and what is the key component that is present for engine downsizing. And the overall objective is, when you're just focusing on engine downsizing, the main theme is to increase the efficiency of the engine and put down the emission to a greater percentage. So one such technique of increasing the efficiency and putting down the emission is the advanced combustion techniques. So they have just coined this advanced combustion techniques as ACT. So the better trade-off between emission regulation and improving efficiency talks about the advanced combustion techniques. So advanced combustion technique is a novel combustion concept which makes a possible option to reduce NOx and PM simultaneously. So you should be able to clearly understand about the soot NOx curve initially. So when you're able to understand the peninsula of soot and NOx in an optimal percentage, then you can just understand this advanced combustion technique in a very much better way. So this talks about the equivalence ratio. So with the equivalence ratio is nothing but the ratio between the actual fuel air to the stoichiometric fuel air ratio. So when it is exactly 1, it means that you are in the stoichiometric point, and when the values keep on increasing, that means your mixture is getting rich, and when the values falls below 1, you are getting a lean combination. So for this particular point of time, when the combustion temperature is between the range of 1800 to 2000, there is an higher possibility of formation of soot. And at the lean mixture combination and the temperature range between 2200 to 3000, you are higher possibility for the formation of oxides of nitrate emission. So the conventional diesel engine combustion, that what we have coined it as CDC, is having a maximum percentage of share in both soot formation and knot formation. So this advanced combustion technique talks about the area between the soot and the Knox Peninsula. So the in-between zone is what focused in this advanced combustion concept. So here what we'll be trying to do is we'll be trying to reducing the NOx and PM simultaneously. That means you need to focus on the area in between the soot and NOx profile. So this is what our area, the area we need to focus on. So it talks about the maximum combustion temperature and creating vector mixture of fuel and air. So in combustion chamber during the combustion process by retaining the acceptable thermal and combustion efficiency. So one such techniques is the low temperature combustion. So in case of low temperature combustion, what we'll be trying to do is they'll be focusing more on the massive EGR percentage rather creating a better fuel air mixture. And next one is the homogeneous charge compression ignition engine. And next one is premix charge compression ignition engine. So let's start with the LTC initially. So the massive EGR percentage or LTC is nothing but creating reduced NOx and better mixing than your advanced or existing CDC combustion concept. So the outline LTC region exists on low temperature range between 2000 Kelvin and the local equivalent ratio of 4. So when you just see this particular curve, the maximum range lies between the equivalence ratio of 4 and the maximum temperature range lies well below 1200 degree Kelvin. So this put together would be able to reduce the NOx by a greater percentage. So for reducing this NOx to a greater percentage, the percentage of EGR in this particular LTC would range between 50 to 70 percentage. So it might vary from 30 to 70 at a maximum percentage. Normally it will be closer to 50 percentage in case of your LTC. So LTC seeks an simultaneous reduction in NOx and soot formation through which the decreased combustion temperature would be able to achieve, and decreasing the combustion temperature and thereby reducing the thereby enhancing the better mixture would able to avoid the soot formation to a greater percentage, and dilution with the air or exhaust gas would create a better EGR circulation, and this would be able to reduce the high temperature zone in the entire combustion chamber. All put together, you will be able to switch over, or all put together, you will be able to just lay off the region of NOx formation and have a better combustion in between the soot and NOx profile. So this what is the earliest stage of advanced diesel engine combustion concepts, where we'll have a better trade-off between NOx and soot. And extensive research are also done with respect to the EGR-based LTC-based combustion techniques. So effect of increasing same biodiesel content on combustion characters of HC emission in high EGR, low temperature combustion. So once you increase the EGR percentage, obviously it would result in low temperature zone formation, and thereby you will be able to achieve a low NOx formation at any point of time. So the main objective is they have deal with only a single injection, and they have slightly varied the crank angle degree of your start of fuel injection for a different load condition. So when you just see this particular case, so this is the start of low temperature heat release rate, and it is the crank angle 5 degree and crank angle 50 degrees. So crank angle 50 degree must lie between the temperature zone of -5 to 5 degree. And after that, you will have the high temperature heat release rate and the burnout condition. So in case of low temperature heat release rate, what actually happens is this would result in a better mixing. So this better mixing would pull down the soot emission to a greater percentage. And after that, the low temperature combustion formation would result in the reduced NOx formation. All put together, you can just have a reduced soot and NOx trade-off. If you are able to achieve a better soot and NOx trade-off, it would result in an enhanced thermal efficiency. So this what talks about the low temperature combustion concept. So where you can just see the start of low temperature heat zone. From there, the negative region in your overall heat release rate profile. And after that, based upon the flame propagation and flame acceleration, that would be able to achieve an higher heat release rate in the later part of the case condition. And this mixed limited condition in the overall heat release rate profile talks about the unburnt or improper mixed fuel that is present in your compression stroke, sorry, in your power stroke. So next, people have started to focus on even further more advanced combustion technique. And one thing they have tried to understood that just by introducing the EGR percentage to a greater level, you can just try to pull down the NOx emission to a greater percentage. And for better result in reduced soot formation, you need to work on advanced fuel injection part. So you need to work on the better interaction between fuel and air. So just to have a better interaction between fuel and air, people have tried to started to think about the early injection timings with the elevated EGR percentage. So the EGR percentage would be as much higher as 50%, and rather in most often cases, we will be trying to inject the fuel between 23 degree to 25 degree before top dead center. So people have tried to start to think about injecting the fuel even in the suction stroke or at the earliest stage of your compression stroke. So thereby the advanced combustion techniques come into picture. One is the homogeneous charge compression ignition engine. So the homogeneous charge compression ignition concept presents the early injection of the fuel, in which the fuel would be injected at a crank angle of 160 to 120 degree before the top dead center. So 160 to 120 degree before the top dead center. So this is the top dead center, which is around 360 degree. So from this before 160 to 120 degree. So that is before, for an assumption here, I have considered 200 degrees. So your diesel is injected merely 200 degree before the top dead center. So that would be more or less your end of suction. So that would be more or less your end of suction So it would be more or less the resemblance of your gasoline engine. So that is the reason why they have coined this engine or this particular technique as homogeneous charge compression ignition engine, where you will be trying to inject the fuel at the suction stroke itself. So thereby there would be an higher option for forming better fuel air interaction, and all put together with an enhanced ETR percentage. You can just reduce you can just eliminate the locally rich air condition mixture and reduce the PM emission, and the higher EGR percentage would result in low NOx formation. So here I have just present you the um, pictorial image of the in-cylinder combustion. So this is a conventional diesel engine combustion, which is yellow in flame. That means it is highly heterogeneous in nature. And focusing on the LTC, it is more or less blue in color. And ideal HCCA is having a complete combustion part. So the only disadvantage in this HCCA is that there is an higher possibility for the formation of CO and HC emission to a greater percentage, because there would be an higher possibility for formation of knocking as you are trying to inject the fuel well before the suction stroke itself. So there would be a better fuel air mixture, and the sufficient amount of temperature might not be attained at that particular point of time. So that is the reason why the profile of this LTC is falling well below the 1400 degree Kelvin. So when the temperature falls below 1400 degree Kelvin, there is an higher possibility for CO or HC emission. So that is one of the greater disadvantage in your HCCA engine. And to overcome this HCCA engine, people have started to think about PCCA engine. So for your kind information, all these are single fuel ACTs. So talking about PCCA technique, in earlier case, we have tried to inject the fuel at 200 degrees Celsius. That is more or less in the suction stroke. And now people have started to inject the fuel not closer to TDC, but in the mid of your compression stroke. So this mid of compression stroke would be either single injection or multiple injection. So here I have tried to make a 3 injection closer in the mid of your compression stroke, that is 90 degree before the top dead center, with an EGR percentage close to 30 to 50%. So whenever you are having an earlier injection and it result in better fuel air interaction, so thereby soot emission would fall down. Next one is, by higher EGR percentage, you can just pull down the NOx emission to a greater percentage. So that result in the reduced NOx formation. So this is the soot peninsula, and here you can just see the NOx peninsula. So in between the zone is what we need to focus much more on. When talking about conventional diesel engine combustion, there is red in color, which interrupts both soot and NOx to a greater percentage. So initially we have talked about LTC, which won't affect the soot formation and knot formation, but it results in a lower thermal efficiency. So next people have started to think about HCCA, but HCCA has an higher possibility for formation of HC and CO emission, because the entire combustion, local temperature combustion zones falls below 1800 degrees Celsius in your peninsula. As of that, people have started to think about PCCA, where PCCA is somewhat better combustion, resulting in better combustion than your HCCA, with an enhanced local fuel air ratio and enhanced temperature range, which would have a minimal impact in the NOx emission, because the overall temperature range is increased as of compared to your HCCA based engine. I hope now you have a clear vision about the soot NOx peninsula and the single fuel ACTs. And this talks about your conventional diesel engine combustion. In case of your conventional diesel engine combustion, your fuel will be injected close to your top dead center. That is, in most often cases, people might have doing research of fuel injecting at 23 degree before top dead center. The main disadvantage in this particular case is that it would result in higher heat release rate and shorter combustion duration. So that would result the thermal efficiency to a greater percentage. And as you are having a higher heat release rate, there's a huge possibility for the formation of NOx. That also might result in an higher soot formation, which would result in a higher rich fuel mixture for the full load condition case. So all put together, these are the greater disadvantage. But to monitor on the combustion phase, the only option that we have in your conventional diesel engine combustion is that introducing shim to vary the injection timing and varying the injection pressure ranging from 200 bar to 300 bar. So these two are the only possible techniques that can be effectively used to vary the injection timing and injection pressure to control the combustion phase in your existing conventional diesel engine combustion, but that can be much more dealt in a better part in your advanced diesel engine combustion. So even the single fuel ACTs fail to a greater percentage in controlling the combustion. So the single fuel ACTs have difficulty in controlling the combustion face to a greater percentage because we are relying on one particular single fuel, either it can be diesel, biodiesel, what of the fuel that you pick, and maintain the combustion stability was enormously tedious, and the operating range was restricted to one particular zone. So extend the operating range towards high load condition is what really impossible. So moreover, they also produce an higher HC formation that we are able to understand because the temperature range is falling below 1800 degrees Celsius, and the formation of CO emission is able to achievable. So this result in incomplete combustion. So people have slowly started to switch over from single fuel ACTs to the next generation ACTs, that is dual fuel ACTs. So it was in 1890 the SI engine was introduced to the human mankind, and 1892 the diesel engine was introduced. After that, people have started to work on turbocharger, direct injection, high pressure injection, variable valve timing, EGR, catalytic converter, and a number of devices to increase efficiency. But even though controlling the CA engine combustion phase was too tedious, so after that it was in 1983 the HCCA was introduced, and 1995 the PCCA was introduced. But the commercialization of HCCA took merely 20 plus years to get commercialized. It was commercialized in only 2007, and after that the RCCA engine comes into picture. So the dual fuel ACTs are introduced as a single fuel, an advancement to the single fuel ACTs to better control the combustion phase by utilizing two different fuels into the combustion zone and maintaining the same case of low NOx and PM emission. So thereby the RCCA and pilot fuel dual fuel injection comes into picture. So in case of your pilot fuel, what would be have is you will be injecting the diesel closer to the top dead center, and the EGR percentage lies between 40 to 50 percentage, and you will be trying to injecting the gaseous fuel at the end of your suction stroke or even at the suction stroke. So this is what talks about the dual fuel engine. And talking about the RCCA engine, the injection timing would not be closer to TDC. You will have a different injection timing than the previous case. So either it can be in PCCA mode or HCCA mode, or it can be either single injection or split injection based on mass injection, based on timing. There are n number of classifications that falls under this RCCA category with clubbing the single fuel ACTs. So in case of RCCA, the combustion could control it would be able to control the combustion phase with a better fuel reactivity and the formation of stratification, and it would be able to control the fuel mass ratio between the high reactive fuel, so that is either it can be diesel, biodiesel, whatever it is, and low reactive fuels such as alcohol and gases would be highly preferred. The process involves introducing a low reactive fuel into the cylinder at the suction stroke itself or at the time of intake manifold. So create a well mixed charge of low reactivity fuel with the air, so that will pull down the soot formation and have a better EGR percentage, and high reactivity fuel will be injected close to the top dead center or at the mid of your combustion stroke. So this can be either single or multiple split based on mass, based on timing, and based on different strategies. You can just try to inject this particular fuel into your combustion stroke. So this is what talks about the RCC. So we need to thank the University of Wisconsin Madison and their engine laboratory for the invention of RCC engine. So particularly the overall credit goes to Kako John, so who was initiated this particular engine RCC engine idea in the 2008. So here he was just using both the low reactive fuel and high reactivity fuel, and with that he was able to control the combustion phase to a better percentage than the previous advanced technique. So here the low reactivity fuel would be trying to inject along with the air into your combustion zone. So the air fuel mixture would be placed inside your diesel engine. Just by introducing the high reactivity fuel, the ignition would get ignited, and that would result in lower soot and higher NOx emission. So they have tried to achieve an efficiency of close to range between 40 to 50 percentage. So that's what they have just reported, working on one particular speed condition and load condition. So this is based on an experimental data based on their own experimental condition. But with this, we can just able to achieve a very high thermal efficiency with reduced soot and NOx percentage. And talking about pilot fuel diesel engine, so in this particular case, it is nothing but a modified diesel engine. So in this existing diesel engine, what we'll be trying to do is we will be trying to inject the gaseous fuel into your intake manifold, and you will have the EGR. So this EGR can be either high pressure, low pressure, cold EGR, hot EGR. There are different types of EGR, but overall objective is to pull down the temperature and have better fuel air mixture that result in reduced soot or PM emission and increased and reduce NOx emission to a greater percentage. So the overall objective of Euro 6 norms talks about 0.4 gram per kilowatt hour, and PM talks about 0.01 gram per kilowatt hour. So yearly it was of around 2.7 of HCCO and 0.97 of HC plus NOx and 0.14 of PM. But now people are not even targeting about the HCCO or even NOx. So they are just focusing more on only PM emission. So that has just stepped down from 0.14 to 0.01. And NOx is not as of now coupled with HC for the emission. So initially the NOx was not taken into account, and as of now the NOx percentage have reduced from 0.5 to 0.4 at this particular point of time. So all put together, we are just focusing more on the emission parameter, particularly in the BS6, and even further emission norms would be much more stringent. So to rely on much more stringent emission norms, we need to focus on more advanced combustion technique and develop ourselves to make this internal combustion engine alive for the next upcoming years. So I have just given you a brief study data that have done all these in one single case. So CDC, where the fuel will be injected close to TDC. HCCA, the diesel would be injected in a suction. PCCA, you will have a 3-split injection in the mid of your compression. And pilot, you have gaseous fuel in the intake and diesel closer to top dead center, gaseous fuel in the intake, diesel more or less in the mid of your compression. So these are the 5 modes of your operation. So this will give you the pictorial representation of the experimental study. So this is the EGR, natural gas percentage. For the single fuel ACT, HCCA, your start of injection would be minus 200, and PCCA, it would be in the mid of your compression, CDC closer to top dead center. And for pilot fuel and RCCA, the percentage of natural gas would get varied, and RCCA is more or less the resemblance of your PCCA, and CDC is more or less the resemblance of your existing CDC. So modified diesel engine is nothing but the pilot based dual fuel. So for this experimental study, I have just considered a combustion chamber which is re-entrant in profile. So I believe you are very much aware about the re-entrant path. So that would have better fuel air interaction and reduce the soot emission. That is what we are very much aware. And have massive EGR percentage, closing ranges from 30 to 50 percentage. And you will have a gaseous injection, and I have just make use of cold EGR, and which is actually an high pressure EGR in this particular case. Based upon this particular study, both the combustion performance and emission data has been carried out. So start talking more about the combustion parameter in a broad way. Here I have just presented the crank angle 50 of the engine case study. So if you just see this crank angle percentage 50, it should be closer between the range of 5 to minus 5 degrees Celsius. When the crank angle 50 percentage is reaching its peak between minus 5 to 5 degrees Celsius of your overall entire crank angle, that means it would result in an enhanced thermal efficiency. So if you just see the CDC percentage, it has just been optimized for the formation of 5 degrees Celsius after the top dead center, and that would be able to achieve in both your pilot field DF. But when you're just moving from CDC to PCCA, the crank angle percentage is falling even to minus 14 degrees Celsius. So this result in a deteriorate part of combustion. When there is a deteriorate part of combustion, it would result in higher formation of HC and CO. So we will be able to understand it anyhow in the upcoming slides. So PCCA is blue in color, which ranging the crank angle of minus 14 degree, and HCCA is even further. But just with an aid of CDC or pilot field DF and RCCA, you will be able to achieve a better crank angle 50 portion, that is either between ranging between minus 5 to 5 degrees Celsius. So thereby it may result in superior thermal efficiency. Sorry for it. CDC could easily control the combustion phase by adjusting the injection timing and obviously in the injection pressure. So just by varying the shim, you can just try to control the combustion in case of your CDC. But talking about the premixed charge compression ignition engine and HCCA, the advanced combustion phase towards the top dead center would result in lower thermal indicator efficiency. So anyhow, it won't be able to vary it, even though if you just try to vary it based on the different crank angle, you're just able to see the color of blue formation in this entire zone. So all put together, it means that it would result in a lower thermal efficiency, and obviously the HC and CO formation would be enormously high. And talking about the RCCA and pilot fuel diesel engine techniques, so this would control the combustion phase more easily by adjusting. You are having two fuels at this particular point of time. You can just either vary the injection timing of your diesel fuel or high reactive fuel, or vary the flow percentage of your low reactive fuel. So that would be able to result in superior combustion phase control with an aid of your dual fuel ACTs. And talking about pilot fuel ACTs or uh, RCCA, the combustion phase was advanced when advancing or moving towards the TDC. So the diesel injection timing at the same time of your EGR percentage. When you're just trying to advance the injection timing and increasing the primary fuel injection, you are able to see the formation of green color over here. So that means it is having a better CA50 part, that is between 5 minus 5 to 5 degree crank angle. And RCCA says that when you're just trying to retard it and increase the EGR percentage, there is a higher possibility or formation of green in color. So that is between 0 to minus 5 degree crank angle. So this is the idea behind the CA50 profile over here, and that would result in superior thermal efficiency. And next talks about the ignition delay. So the ignition delay in your conventional diesel engine is somewhat nominally good, because the conventional diesel engine is already optimized for its existing operation. So the ignition delay in your conventional diesel engine would vary from 8 to 15 degree crank angle. So the conventional ignition delay CDC is having a lower ignition delay, followed by the PCCA. They are just trying to couple it, dual fuel PCCA and RCCA, they are trying to couple it. So in between this particular zone, the CDC or either dual fuel ACT result in an optimal ignition delay. But when you just try to inject the fuel merely 90 to 100 degree before the top dead center, what actually happens is that the ignition delay would get increased. As if you're trying to inject the fuel well before the top dead center, what actually happens is the temperature inside the combustion zone would be very minimal. So that won't be able to convert your liquid into vapor and create better fuel air mixture. So that is the reason why there is a formation of very high ignition delay at this particular zone, and even it would reach its peak, particularly in HCCA, because you are just trying to inject the fuel even at the suction stroke itself. So when you're just trying to inject the suction stroke, think about the pressure and temperature inside your combustion zone. So all put together, the ignition delay would be enormously high when talking about HCCA and the later part of your PCCA. So ignition delay was increased by advancing the diesel engine timing in all combustion chambers. And in terms of burn duration, so that is normally CA10 to CA90. So the burn duration should be as short as possible. So the burn duration should be as short as possible, resulting in a superior thermal efficiency. So the duration would be stated between minus 5 to 90 degrees Celsius. So the longer burn duration would deteriorate the thermal efficiency. That would be a huge possibility for heat transfer losses and lowering the constant pressure combustion part. And there is an insufficient region between 100 to 120 degree before TDC. So this is the particular zone. So that what here I have mentioned. So particularly between 170 to 100 degree before TDC, where that relies on HCCA PCCA concept with very low uh, burn duration. That means the burn duration is enormously high. So that is merely 50 degree crank angle. So if the burn duration is enormously high, it would deteriorate the combustion to a greater percentage. So you need to try to sync all these parameters in a single unit. The burn duration is higher, the ignition delay is higher, and the CA formation over this particular zone is enormously high. So all put together, thermal efficiency will fall down, and that would result in higher HC and CO emission. And next, talk about the COV IMEP variation. So the COV IME variation should not exceed 5 to 10% of an individual cylinder. So CDC recorded a minimal percentage of 1.5%. So this 1.5% is more or less reliable for CDC and dual fuel combustion concepts, but merely till 80 degree before top TDC, PCC would be able to sustain. But after that, the percentage is getting varied from 5% to 13%. So all put together, the thermal efficiency would fall down. So the CDC is nothing but the formation of HC percentage in the overall combustion zone. So unburned HC level of 5000 ppm wet at actual CO2 level. Sorry, actual oxygen level. So that what is talks about the COB IMAP variation. So if the variation is too higher, it would result in an incomplete combustion formation, putting down the thermal efficiency to a greater percentage. And next is the engine durability study. So this engine durability study talks about the maximum pressure rise values between the previous pressure and crank angle values. So if this pressure and crank angle values exceed 10 bar per degree crank angle, it would result in higher vibration and formation of knocking in your existing engine. So when you just see this very keenly, only in PCCA and in the mid part of your dual fuel ACTs that result in very low percentage of engine durability, engine noise and durability study. But either in CDC or in the earlier part of your advanced dual fuel ACTs that result in higher percentage of the peak release rate, the maximum peak rise rate. So that result in an engine irregularity creating excess noise inside the engine. So MPRR was recorded extremely high, nearly 20 bar per degree crank angle. So which is enormously high because the maximum limit is only 5 to 10. So nominally it would be vary from 8 for your CDC. If it is moving to 20, that means the engine would be keep on vibrating. So if you just try to vary the injection timing, you can just work on these particular noise and engine durable study with respect to your maximum pressure rate curve itself. Next, moving into the emission part. So our key objective is focusing on the soot and NOx trade-off. The soot and NOx trade-off, and you just see the NOx formation as the thermal efficiency of CDC and the earlier stage of PCCA or dual fuel PCCA result in superior thermal efficiency. So thereby the NOx formation is enormously higher in this particular zone. Whereas when you're just dealing with PCCA or the later stage of PCCA, you can just able to achieve a very low NOx. Here you can just see the NOx percentage is very minimal. So the optimal NOx percentage that has been suggested is 0.4 gram per kilowatt hour. So when you're just focusing only on NOx, you can try to run your engine either in this particular zones. But for better efficiency, you need to focus on the zone in green in color. And when you just see in soot, in most often either single fuel ACT or dual fuel ACT, you will be able to achieve a very low soot formation because you are varying the injection time. But only on certain particular zone of your PCCA, there is an higher possibility for the misfiring issue. So that would create an higher soot formation because of the in-temperature combustion inside the combustion zone. So that what talks about the NOx and PM trade-off. And here I have also presented the HC and CO formation. So the HC and CO formation for your advanced diesel engine combustion techniques says that the HC emission for your CDC is very low because the thermal efficiency is higher, and the PCCA would also result in lower HC formation. But dual fuel PCC would result in lower HC formation, whereas PCCA and HCCA result in very low thermal efficiency and increased HC and CO formation. So there is a greater disadvantage when on your HCCA and PCCA based engine, and that is also having the resemblance profile in your CO emission. So the main reason is the blow through, the crevice, and the bulk quenching. So this bulk quenching result in higher HC and CO emissions in your single fuel ACTs, particularly on PCCA and HCCA. That can be very much controlled when you're just moving to your dual fuel ACTs. Moving on to the next experimental study, there is nothing but the thermal efficiency. So the indicated thermal efficiency for your CDC is closer to 44.3. Make a note, it is indicated thermal efficiency. I have not calculated the brake thermal efficiency. So indicated thermal efficiency is closer to 43.3, and that particular zone is having a regional impact on the dual fuel PCTs also, but the thermal efficiency would be very much lower, particularly in your later stage of PCCA and completely in the HCCA zone. So the thermal efficiency of your HCCA would be enormously high, but focusing on NOx, HCCA is the best option. And focusing on thermal efficiency, HCCA is the worst option. And fuel consumption would also be enormously high in your HCCA and PCCA zone, resulting in very low thermal efficiency. And talking about the in-cylinder pressure, here I have presented the HCCA as it is having two injection. One is at the mid of suction stroke, and the main injection would be closer to top dead center. If that is the case, we'll have two peaks present in your P theta and heat release rate profile. And this will give you the entire plot of this particular study. So when you're just focusing on CDC, you will be able to result in superior PM formation, superior NOx formation and very low PM formation. But when you're just switching over from CDC to PCCA, the NOx formation is very much lower, but there is a nominal soot formation. From PCCA to HCCA, you can even further step down of NOx, but the PM formation is higher. If the PM formation is higher, it would result in higher HC and CO formation. And when talking about the NOx emission, when talking about the dual fuel PCCA, you can drastically reduce the PM emission and soot emission. So that is what the RCCA and advanced fuel dual fuel DCDs are highly interested at this particular point of time. And talking about indicator thermal efficiency, you will have a better thermal efficiency than compared to your conventional diesel engine combustion, and the combustion efficiency would be more or less same. And the COB IMEP percentage is also well below the 5%. So that would result in better combustion data for your advanced diesel engine combustion. So the main takeaway from this particular presentation is that when you are just focusing on single fuel ACT, you will be able to achieve low NOx and superior PM reduction, but it would be very hard to control the combustion phase, and it would result in lower thermal efficiency, higher CO2 formation and limited operating range condition, and higher HC and CO formation. But switching from single fuel AC to dual fuel ACT, you'll be able to reduce from low NOx and PM, and you will have better combustion phase with the diesel, because just by varying the injection timing and pressure, you can just try to control the combustion phase in your dual fuel ACTs, and the thermal efficiency would be closer to the CDC, that is the existing engine, and or even somewhat slightly higher, and CO2 reduction is able to achieve, but only condition is it is limited to the low load condition. You can't run this advanced combustion technique for high load condition. It would result in once again the same soot formation, and this might also sometimes result in higher HC and CO when you are just operating in the high load or full load condition. So this is the key takeaway from this particular presentation. I hope I didn't bore you much in this particular presentation, giving certain information about advanced combustion techniques that is present at this particular point of time in the hybrid vehicles. And these are the different literatures that I have currently gone through to make this particular presentation. And even I am also happy to share my latest article that I have gone through, or I have published in Journal of Clean Air Production with respect to the CDC, HCCA and PCCA for better understanding also. So now the session is open to the audience for the queries. And if you want to Google about me, you can just Google by this particular name as Dinesh Balasubramania. And I have also shared my email ID and contact number for further research interaction. Now the session is open to the audience for the queries. Hello, sir. Hello, sir.
Hello, sir.
Sir, whether am I audible? Ah, yes, sir.
Hello, any question? Hello, any question, please?
Hello, sir. Hello,
Hello, sir.
sir, audible?
Yes, sir.
Sir, we can use additives for this one, sir. Higher alcohol additives.
I could. Yes, sir. You can just make use of it. It would be a low reactivity fuel.
Sorry, sir.
In your dual fuel ACT, you can just make use of low reactivity fuel. So the main objective of low reactivity fuel is at the time of suction, the overall pressure and temperature would be very minimal. So you need to make use of lower boiling point fuel at the time of your intake suction stroke. So that is the reason why people are preferring either gas or alcohol-based fuel. So it would have a very low temperature of converting from liquid to vapor phase. So that would make you will have better fuel air interaction. So that is the reason why alcohol-based fuel are used in your intake stroke, but using as an additive will not give you a better efficiency in case of your dual fuel ACTs.
Is there any effects for combustion? Once we use, for example, pentanol, higher alcohols.
Yes, you will have better interaction. So that's what I'm saying. The dual fuel ACTs, the key objective is that using low reactivity fuel in the intake stroke. So the low reactivity fuel should have low boiling point. So pentanol, hexanol, butanol, all are having low reactivity or low reactivity, can be treated as low reactivity fuel. And as their boiling point is very minimal, that would be able to convert from liquid to vapor phase at the process of your suction and compression stroke. So you'll have better air fuel mixture at the end of your compression. And when you try to introduce this high reactivity fuel, there's a huge possibility for a better combustion, better homogeneous combustion. And that would obviously increase the efficiency. So you need to focus more on this fuel, that is low reactivity fuel with very low boiling point. And it should not be very low. So that would create a cooling impact inside your combustion zone, and once again the combustion would get deteriorated. So what is the mass of fuel that is you are going to inject, and what is the either you can just heat it at, and also inject. So heating the inlet temperature, extensive studies are going on this particular direction. But I have just given you a brief idea about it. I believe I have answered for your question.
Okay, sir.
Any questions, sir? Any other participant? Any other questions? Okay, thank you, sir.
Thank you very much, sir. So I would like to thank once again the head of the institution management and the organizers for giving such an interesting opportunity to explore my perspective on advanced diesel engine combustion technique, particularly for a cleaner combustion. So for any future interaction, you can just ping me through this mail ID or contact number at any particular point of time. Thank you very much, sir. Have a nice day.
Thank you, sir. Thank you, Dr. Dinesh Subramanian, sir. Thank you for your presentation. It was very helpful, sir.
Thank you, sir.
Sir, any other participants, any other questions? Okay, sir. Thank you, sir. We are about to end the session.
Okay, sir. Thank you very much.
And and as you all know, tomorrow at 9:30, the session will continue at tomorrow at 9:30. Okay, sir. Thank you, sir. We are going to end our session here only. Is there any doubts? Any other participants, sir? Okay.
No, sir. No doubts.
Okay, sir. Okay. Thank you for your presence, sir. Thank you, and let me remind once again, tomorrow at 9:30 we are going to start the session. Okay.
Thank you, sir. Thank you.
Okay, thank you, sir.
Thank you, sir. Thank you. Sir, shall we leave?
Okay, sir. You can leave.
Okay, thank you, sir.